let's start again. I hope you had refreshments. You are refreshed. And let's deep dive into the hardware aspects, so to say, of the future of computing. And in this session, we are looking at different approaches and different views on the material side of next generation computer chips. And we have 4 internationally renowned speakers for you today. The first one from Fraunhofer in Freiburg. I'd like to welcome on stage Peter Knittel. Welcome, Peter.
So, you can hear me? Yeah. Thanks for the kind introduction. I also like to thank Professor Jens Eisert for breaking the ice in terms of quantum computing, maybe also breaking something else. But he gave a really nice introduction on why quantum computing is exciting. And now what I want to do is I want to dive a bit deeper into some technology aspects, especially material aspects. And as from our history at Fraunhofer IAF, we've always worked a lot with diamond. A lot of people will know it from jewelry, but we use it for quantum technologies. And there is also the perspective to use it in quantum computing. And there are some advantages and challenges, and I want to point out these in this short presentation. So maybe just at a quick glance, who we are and what we're doing. Fraunhofer IAF is located in Freiburg, so quite a travel from Berlin. We are one of the oldest Fraunhofer institutes, actually the 5th that was founded. And our main focus is on materials, in particular 3-5 semiconductors, and also diamond. We also have a group working on quantum algorithms recently. We are working with the IBM System Q in Ehningen. But today I will mainly focus on the diamond-based technologies. Okay, maybe first of all, let me quickly remind you of the DiVincenzo criteria for a qubit, because this is important for material that wants to realize qubits. What do we need to get a good qubit for computing? We need a scalable physical system with well-characterized qubits. We need the ability to initialize this qubit in a state, in a defined state. We need long relevant decoherence times. That means we need long time for calculations, and this has to be longer than any gate, for example, C-NOT gate that is done. We need a universal set of quantum gates that can be implemented, and qubit-specific measurement capability. So this is the prerequisites for any system that wants to implement qubits. As a short overview here on the current systems, I took this table from Inside Quantum Technologies. You see that every system that is available on this chart, there are probably even more, has some advantages, has some disadvantages. This was already mentioned before. There is probably at the moment not a perfect system on the market that only has advantages. Why are we using diamond, or do we want to use diamond? Diamond has, and a lot of people know that, a very rigid structures. It's an ultra-hard material. This offers the opportunity to include quantum states in the diamond, in the case of color centers, for example, and they can be operated at room temperature or close to room temperature. So this would allow for quantum computation or quantum manipulation at room temperature, and could make, for example, also a mobile quantum computer possible. So what is a color center in diamond? I will now talk specifically about the nitrogen vacancy center, which is basically a nitrogen atom that sits on a carbon place, and besides the nitrogen there is a vacancy, and in this vacancy we have an electron, a free electron. We've heard about atoms being used for qubits. Here we can use this electron as a qubit because we can manipulate this electron. The electron can be excited using green laser light, and by exciting it in an excited state, it overgoes system crossing if it's in a specific spin state, and all the electrons are then pumped into the MS0 state. So we can initialize it in a certain spin state, in this case the MS0 state. There are two other states that can be used, or at least one other state that can be used by microwave driving, so we can have this two-level system, MS0 and then MS plus minus 1. I have to note here that the MS plus minus 1 system under a magnetic field splits up, and this allows for actually detecting magnetic fields, and this is done in quantum sensing applications that I will not talk about today. So the spin state is then basically read out by this red fluorescence, and the point is, if the system is in the MS plus minus 1 state, the emission in red will be decreased. If it's in the MS0 state, it will be at a constant level, and this also leads to this nice red color of diamonds with lots of NVs. This is actually, the image here is not the true size. Typical diamond substrates are 3 by 3 millimeter, maybe 5 by 5 millimeter, but not wafers. We have some unique properties that are already talked about, but one is that the spin coherence time at room temperature can be in the range of milliseconds. If we go and couple with a nuclear spin nearby, we can reach seconds of coherence. That means we have a computational time of seconds. In comparison, superconducting qubits are typically in the 100 microseconds range, can also go up to milliseconds, but in this case at close to 0 Kelvin. How can we integrate these NV centers into diamond? There is a straightforward approach that is used still for, to quite an extent. We just use a nitrogen gas source basically and implant the ions into the diamond. If you're working with materials, you will know that implanting ions in diamond will lead to some, or into materials will lead to some damage to the structure. This is also true. There are some means to actually circumvent these problems, but for diamond there is nothing that you can do, like for example a thermal treatment that will heal out all the defects, unfortunately. So you will have to live with some of these damages, and these will actually decrease the coherence time. So this is one approach. It's working perfectly to make individual NV centers, but at the cost of a bit of coherence time. Another approach that we are actually following is the integration via growth. So what we can do is we can grow nitrogen into the diamond during a CVD process, so the diamond is grown by chemical vapor deposition. With that, we don't only control the integration of nitrogen, but also control the surrounding of the nitrogen, meaning that we can actually use isotopically pure gases, which lead to less decoherence due to nearby nuclear spins. Or we can actually position nearby nuclear spins for some reasons that I will show on later. Problem is, this is a statistical process, and it's really hard to obtain single NVs here. A big advantage here is that we not only can make these NV centers in the diamond, we can also orient it along the growth direction. So we will have a preferential alignment of this NV center, which is in principle a 2-atom system. This is not possible by implantation or any other means. So now with very thin films, we can localize in the NV center in the diamond, but there's also a possibility to do a lateral placement by growth. You can see here a small microstructure that is overgrown, and using certain parameters, what you can actually do is during the overgrowth, you can dope these facets with nitrogen. As these facets are 1-1-1 crystal facets, the NV center will lie orthogonal to these facets, and this can be seen here. This is actually what you see if you drive the system to the ms plus minus 1 state. So there's a magnetic field applied. As soon as you reach resonance with the ms plus minus plus state or ms minus state in this field, you will see a dip in fluorescence intensity, and depending on how much on the orientation of the NV, it will see more or less of the magnetic field. And this is why each orientation on this pyramid has a different feeling to this magnetic field and has a different splitting of the ms plus minus 1 states. You can also do this in an inverted approach and fill holes. Same principle. You will have an inverted pyramid, and with that you can go down to a few hundreds of nanometers in positioning accuracy at the moment. So this is a way to accurately position via growth. So let's talk about quantum computing with diamond NV centers. At the moment, there are products already available. We're not speaking about large qubit systems with like the IBM system that we've heard of already that reached almost or more than 400 qubits. We're speaking about systems that can reach maybe 8 qubits in reality at the moment. There are perspectives that even 50 qubits are feasible. But what is commercially available by companies like Quantum Brilliance, SexNQ, and XeetQ is a 4 to 8 qubit system. Here, the NV center is not used as the qubit right away. It's actually the surrounding 13C nuclear spins that are used as the qubits. As we've heard, the nuclear spins have longer coherence times. But what we cannot do is directly address them. We're using the NV center to address these nuclear spins in the surrounding, and we just use the NV center as an initialization or control and readout mechanism. So this is one approach. Obviously, you cannot scale this up. You cannot just put millions of 13C carbon spins around the NV center and still individually address them. That's not possible in that case. That's why actually you need to couple the NV centers that you use for readout. You need to couple them either dipolar, so they have to feel each other in a dipolar coupling, but that means they have to be positioned in 10 nanometer distance from each other. As you probably know, this is to date probably not even feasible to do like electronics on that level in an easy way. So positioning it via growth or implantation is also not that easy. There are means to do this. One problem is addressing them, as I spoke about the optical addressing. Optically, we are limited to the diffraction. So there has to be a readout system that is shown here. They can also be read out electronically, but this is just a side note. So this could be possible, but it's very difficult to be implemented. There is another way that combines actually the photonic approach that we've heard already and the spin-based approach that I was talking about. Is if you couple these color centers into a resonator device, you can actually use the photons emitted or brought into a waveguide by this resonator device to entangle them, these registers individually. So this is an approach that we're following actually in one of our BMBF-funded projects, spinning. Here we are not using NV centers. This is the emission of an NV center. This is the emission of a so-called silicon vacancy center. The difference is the silicon vacancy actually lies in between two vacant positions and has an inversion symmetry. So the emission is sharp at 738, whereas the NV center has a strong phonon sideband. This is important if you want to couple it to a resonator. You have to make sure that the photons that are emitted from the resonator are indistinguishable. So this is a challenge. Problem with SIVs is, you see here, this is 10 Kelvin. You cannot use them anymore at room temperature. So this is another approach that we're working on that may actually lead to larger systems, apart from the dipolar coupling that still has challenges in positioning accuracy. How can such photonic devices be fabricated. Actually, what you see here are freestanding diamond waveguide systems, like ring resonators with waveguides. You actually see that even in such simple ring resonators, you get, this is actually from the NV, you get resonances to the ring. You see over the whole phonon sideband some resonances. So with that, you can fabricate devices that actually strongly enhance the zero phonon line or the emission of the NV center, and this makes sure that you actually can entangle these photons in the end. So this is already possible. It has been shown with different resonator devices, and yeah, they can be fabricated nowadays with high Q factors. This is not the issue anymore. One of the issues is actually positioning these color centers in the resonator devices. And as you see here, actually, this is a full diamond chip. Still, we're having this issue of rather small diamonds being used. So single crystal diamonds are only available in small sizes to date. So I want to summarize here what are the main challenges. I think one of the main challenges for all quantum computing tasks with diamond are actually accurately positioning NVs or other color centers, and this is what we are working on strongly. One other thing is the readout that I mentioned briefly. Fabrication of these high Q photonic structures has been shown, but still needs some testing and probably will benefit from larger diamond substrate sizes. So this is actually a 2-inch wafer that was fabricated. It's not that nicely shaped as a silicon wafer, but it is possible to get to wafer size diamond. There are some backdraws, but we can discuss about these maybe at a later stage if you want. And with that, I'm at the end, I think. I hope I gave you a brief introduction into diamond-based quantum computing, and looking forward for questions at the end of the session. Thank you very much.
Thank you very much, Peter.